We have one more hypothesis test to learn about in statistics, and that is a paired t-test. So sometimes data can be paired together. Maybe they take a sample and they do two measurements. I wrote two observations, but this is sometimes like two measurements on each subject. So if they do that, where there's two measurements found on each subject, and you can scroll down and look at the example below. There were two tests performed on each subject down there. Many times they'll do like a before and after score or test. The next part of that sentence, if you can somehow link two subjects together and they each got a different treatment or whatever it is you're measuring, then you could arguably have paired data that way also. So when you're doing this, we call it a paired t-test. And for our hypothesis, we are going to assume that the mean difference is 0. We're going to assume that there is not a difference between the two. And we're going to test to see if there is one. Maybe something negative when we subtract them, maybe something positive, or just plain old not equal to 0. For the do step, our formula just barely changes. Just put little d's on everything. But everything else is the same. We're talking about paired data, so make sure in your descriptions you talk about the pairing. But that's about it. So let's look at this caffeine problem. They have these people addicted to caffeine. Maybe hit pause and read through it. One critical thing that they did to make this a viable experiment is they randomized the order of giving these two treatments. And it's really important. Notice, first of all, that we don't have a random sample. So that's something of note right there. But they did accomplish some randomness by giving the treatments in a different order, or randomly. And the reason is, let's write this out. Why is this important? If there is an extraneous factor, this goes all the way back to designing a study that we did in the fall, that has an effect on depression, then results are confounded. And if you can argue that this effect is something that all subjects experience, then you have a good example. They may ask for an example. That's actually really hard to come up with, and many times a good go-to is weather. If weather was really nice, I'm going to have to write over that part B there. On the day they received caffeine. This is assuming results were not randomized. So I should write that at the beginning, sorry. If not randomized, sorry, I should have led with that, then all that I just now said. So it's like a double if, I guess. If weather was really nice on the day they received caffeine, low depression might be because of weather. This concept is really important. This isn't even hypothesis testing. This is just designing a study. So this is a little bit of review, this part A. So it's important to control those extraneous factors. One way to do that is random assignment. We talked about that back in the fall. All right, I'm going to have to erase that so we have room to do this hypothesis test, this paired t-test. So you see the data for each subject. You have a caffeine score and a placebo score or depression score for each treatment. So quickly walk through there and subtract placebo or subtract caffeine from placebo. Should be really simple. Just write down your results there. So here are mine. And those are the numbers we need to type into the calculator. The individual scores, we are now done with them. Typically what you'll see in a problem like this is also a graph of the data, and we'll talk about why in a second. So on the state step, we're going to talk about the true mean difference. The true mean difference in depression score placebo minus caffeine. I think it's important to note what you subtracted for people addicted to caffeine. And then for our hypotheses, we're going to assume that there is no difference. And when we subtract caffeine from placebo, we think placebo has a larger score, a larger depression score. So we suspect we're going to get a positive mean when we do this. And then let's let alpha equal 0.05. For the plan step, be careful. This is not a random sample. They were volunteers. But there was random assignment. Two treatments. N is only 11. That's smaller than 30, right? So let's go to our calculator, type in all that data, and look at a graph. On the calculator, here's all my differences. I made a graph already, and I have a box plot here. To be honest, it's not very symmetric. Here's my dot plot. But the crucial thing is outliers. I don't have any outliers, which is good. People say that this t-test is a pretty powerful test, and it can handle some non-normal behavior. So we're going to kind of look the other way on that non-symmetry and just point out that there are no outliers. Maybe, I don't want to say it's not symmetric. Graph is a little symmetric. With no outliers. Distribution is approximately normal. I'm going to run out of room here. I did not give myself much room. All right, on the do step, let's change colors so I don't blend in there. We are doing a paired t-test. I need to get x bar d, that's the mean difference. I need to get SD. I already know df is 10 because it's n minus 1. If you want to write the formula, although we already wrote the name of the test, the formula is this. But let's go to the calculator. So on the calculator, on the spreadsheet, you hit Menu, Stats, and they don't distinguish between t-test and paired t-test. It's the same exact math because you're going off of one list. So click t-test. We have a list of data values. Our null is that there is no difference. I named my list A, and I suspect that they are positive. And there are all my values. Let's write those down, and we can make a conclusion. So my mean difference was 7.3636. My standard deviation was 69177. The t-score was 35304, and the p-value is found by doing proportion of t's larger than 35304, and it was a really small number. Just out of room there. And that is smaller than alpha. All right, so final last step. This is very crowded. I did it pretty good in class. Why did I run out of room? I was writing the state step way too big. We end up rejecting HO. Evidence suggests. The true mean difference. In depression score, whoops, is greater than 0. Caffeine appears to be related to low depression. Maybe lowering. Depression. Oh my gosh. Completely ran out of room. I hope that's readable. Reject HO. Evidence suggests the true mean difference in depression score is greater than 0. Caffeine appears to be related to lowering depression. All right. See y'all later. Bye.